Do you hear me okay from through the mic? Uh-huh. Huh? Correct. You were sitting here?
Huh?
You were sitting here?
Or where was this? Oh, I'm not going to displace you. Come. I don't know about gravitation. So how is the gravitation?
Get started?
Yes, you can wait for a minute. It's 9:30.
30 plus 10, or how do you want to do it? 10, 5.
It says 40 minutes, so I can say 30 plus 10.
30 plus
Maybe
10 or 35 plus 5?
35 plus 5, I think. So I'll
Thank you.
basically let you know
Correct.
10 minutes before and then 5 minutes before.
That's right. Hey. Hey, morning. Okay. Sorry. No problem.
Okay, so let's get started. It's already 9:32. So welcome to the first session of day 3. So the first speaker is Suvodip from TIFR. He's going to speak about learning the universe with cosmic messengers.
Thanks a lot, Gaurav. And let me start, of course, by thanking the organizers for inviting me to give this talk. It's always a pleasure to be back at RRI, and talking on this different topics. I think I don't remember what I spoke last time, but this time I'm going to talk about gravitational wave as asked me by the organizers. And this is possibly the first talk on gravitational wave from astrophysical sources. I'm sure you have heard about gravitational wave from cosmological sources. So there will be a little bit of introduction, but not too much, because it's a short talk. Okay, so let's get started. Let me take you back for last 100 years back and start from there. I'm not going to bore you with that. What I'm going to tell you is it's an exciting time. Cosmology has seen an exciting time from an absolutely theoretical area to a observation-driven science. This image is not made by me. Why there is no galaxy service here? If you should ask the image credit group. All I'm going to tell you about is there are multiple observations. Observational cosmology has started for last 20, 25, 30 years, mainly in the mainstream way, and helped us in building the standard model of cosmology. Great. And in this particular sector, there is always a balance between theory and data. And sometimes it becomes theory heavy, And sometimes it becomes data heavy. When it becomes very heavy, we start calling it speculation driven. Everything we would like to measure. When I was an undergrad and studying first cosmology papers, it was all about omega matter equal to 1. I'm sure many of you have seen the similar papers. I'm sure none of them will be published now if we write it. Other side, if it gets data heavy, it becomes anomaly driven. We start talking about, heard about this in yesterday's talk as well. JWST is seeing something, is it attention or an anomaly? So where is the balance? And in order to get to a standard model of cosmology, which we will in some sense put up books to say people, this is what we have discovered in the last 100 years or more than that, we have to get a balance between the theory and observation side. And this journey was great. I mean, that's why I'm doing cosmology, because we now have a standard model of cosmology, which is really the help of several observations, starting from very high redshift CMB to very low redshift galaxy survey supernova. In between, stuff will be observationally confirmed or discovered very soon. You have heard about it yesterday. What have we learned? Our primary understanding so far are driven by electromagnetic observations across band. And this is our favorite picture of what we understand so far as the cosmic evolution. Something happened which we call Big Bang, and then at least today we understand the universe is primarily dominated by stuff which we do not understand, like dark matter and dark energy. And we have a scenario of particular evolution very well understood over here, and the evolution from here to onwards. What are the pillars on these observations? Of course, cosmic microwave background, 3 decades of experiments, large scale structure, of course, which includes everything which is in the galaxy. You can talk about supernova, you can think about galaxy surveys, you can talk about AGNs, you can talk about quasars. And this really has shaped our, what I call as the standard model of cosmology, the lambda cold dark matter. We have a model where we have to understand all the 4 terms of it. We have to understand what is lambda, what is cold, how cold it is, and how dark it is. And of course, what we really understand that it gravitates, so it has some mass. Moving on, what are the open questions? Did you really solve the area of cosmology? The answer is, of course, no. We have open questions from the Big Bang to the black holes. This is a scenario of the standard model of the expansion of the universe, but if you really ask the open questions, we have open questions from here over here, how the heaviest black hole form, where we see quasars at the highest redshifts. These are open questions since I was in a PhD program, and I came to know that, these are actually interesting for them to work on. And they still remain to be the open problem unless we have some surface at very high redshift to give us an answer. And the question now comes, what's new? What's the next? So I told you about the last 100 years. Now talk about, may not be 100 years, but a few decades. Where do you go forward from this? Is there a better way? Is there another way to probe the universe deeper and better? And that's what brings us to the topic of gravitational waves. Better and deeper in what sector and how? One of the advantages of gravitational waves, so think about it, it's been extremely difficult to detect because it is very weakly interacts with anything. Great. I don't have to much worry about interaction of anything else. I can see gravitational wave from very far away object. There's literally no something called as like optical depth of Thomson scattering like effect, as large effect as that for gravitational waves. And thanks to the huge effort from the engineers to make it possible to really see these sources at a cosmological distances, means outside my galaxy. So I have possible sources which I can see far away, and I can measure them with possibly less number of contaminations. Both are possible at this stage, and we'll see how things proceed from here. Moving on, what it brings to us. Exactly like the way you have electromagnetic spectrum, gravitational wave also comes at a huge frequency band, starting from very, very, extremely low frequency. This is possibly already covered in the first day when you have heard about experimental efforts ongoing on the CMB side. Simon's Observatory is the one which is currently funded, and we expect it to be funded and get the results on the gravitational wave measurement at the cosmological scales. There are other proposed experiments. Some of them are not in its full funding scenario right now, and some of them at the proposal level currently as we speak, or at the level of more like a discussion going on with several possible funding agencies. That's at the extremely low frequency gravitational waves. To ask me more questions about how it is measured and using semi-polarization, happy to discuss about it. But it also has signal at all other spectrum. Some of them are currently more detectable technologically than the other, and that's how these experiments are mentioned. Okay? So next achievable sector is in the nanohertz range, where gravitational waves can be expected from supermassive binary black holes. Okay? Big objects. Big objects merging together to emit gravitational wave. There's an international effort called International Pulsar Timing Array. From my group side, I'm a part of Nanograph, and India is a part of course, INPTA. So this entire effort is ongoing to measure the gravitational waves in the nanohertz range. Moving on to a little low frequency, is to see that, now we come to from nanohertz to a band which is accessible from funded space-based detector called LISA. It's going to see the sky in the millihertz gravitational waves. 3 orders of magnitude higher frequency than here, and 3 orders of magnitude lower mass than here, about million solar mass. I am going to see sources of the million solar mass or a little lower in this frequency band from LISA. And the stuff which has made the first confirmed discovery of gravitational wave happened at the highest frequency with thanks to the LIGO-Virgo collaboration, which has detected binary black holes of the order of few tens of solar mass. And the effort is ongoing. I'm sure all of you have known about the ongoing efforts. So from LVK, of course, there is LIGO India coming up. And in future, there are proposed experiments called as Cosmic Explorer and Einstein Telescope. This is not an exhaustive list. There are many other experiments gets proposed. There are stuff coming over here which people is interested. There are stuff coming over here which is interested. I am talking about more experiments, things which are currently ongoing or already being conceptually developed or demonstrated that it is possible. But what you have to remember, this band can actually exceed to a much higher frequency, and there's a very active effort going from the engineering side to understand how can we achieve it. But what's the take home? Why should I care about measuring gravitational wave being an astrophysicist? I really doubt nobody has seen this slide before, because whoever has heard me speaking on gravitational wave has heard some version of this before. My way to sell gravitational wave to non-gravitational wave scientists is the following. I would say is the length redshift source time scale is this domain where gravitational wave brings a completely new way to study the astrophysical objects. How? I can see sources up to very high redshift. That's not new. That I can do with other observations as well. I have a coherent signal whose theoretically I can predict thanks to Einstein's theory of general relativity, which can vary in time scales from milliseconds, seconds to years time scale. Means LIGO is currently seeing very heavy black holes for a few tens of milliseconds. We can see for a few years in LISA for supermassive black holes or of the order of those masses. Thanks to Einstein's theory of general relativity, how all they will fall towards each other and emit gravitational wave is well predictable. And there's a huge range of sources. Like we talk about galaxies, we talk about quasars. Now we have a range of sources from binary neutron star to supermassive binary black holes, which are potential candidates to observe the sky using gravitational waves of non-cosmological origin. And my favorite axis, as I always say, is this one, where I start learning about physics across length scale. Whether it is at the cosmological scale where gravitational wave is propagating, it gets imprinted by the expansion history of the universe. At the kiloparsec scale, it gets impacted by the galaxy physics. At the parsec and the kilometer scale, it gets impacted by the stellar physics, stellar dynamics, all those things which we don't understand so well. So it's an entire zoo for you to understand whichever hat you wear as an astrophysicist, possibly you have something along this axis to worry about. From fundamental physics at the kilometer scale, when the two black holes are nearest to each other at the strongest gravity, to the largest scale like most people in this room worries about in the sense of cosmology. Moving on, what I would like to tell you is this great opportunity comes with an exciting science cases across the spectrum. I'll talk about a few of them today. It's a very nice cartoon made by Alex, which tells us as a function of redshift and mass, how different detectors going to see. These lines at the horizon means anything beyond it I don't see. So again it will be played. LIGO will be somewhere up to redshift of 1, Cosmic Explorer 40 kilometers about redshift of 100, and so on across different mass scales. That's what I was trying to tell you about in my last slide. So now let's try to move on to a couple of different topics and see in the sector of cosmology, how are we going to do on this. At first, let's talk about expansion history of the universe. Expansion history of the universe is another quantity that is measured 100 years back. 1929 is the first time Edwin Hubble made an observational evidence of universe is expanding. We have not got a value which we all agree upon. So the effort is, can we get it in next before it is 100 years? I don't know. But at least we have effort to understand this in a more data-driven way. Let's discuss about this, how it is possible from gravitational wave observations. It's possible from sources with electromagnetic counterpart and sources without electromagnetic counterpart. And why we really care about this is because as time has progresses for last 20 years, all agreement between the high-redshift probe and low-redshift probes started disagreeing. You may think that this is, whoever is not familiar with this particular topic, is called the very well-known Hubble tension. Is not only a tension about these few data points. This is the ever-growing chart. People have now made it even longer. I stopped putting the most latest plot. It's from 2022 review article. These are the measurements coming from all kind of high redshift probes, agrees with CMU. These are kind of stuff which is coming from the low redshift probes, agrees with something or the other. And there are few measurements here on the gravitational waves, a few of our works, that I am going to focus now. So what is the big deal about measuring expansion history? The problem is length scale. It's extremely difficult to measure length, particularly when it's an absolute length measurement. Why do I care about it? A ratio of the absolute distance and the velocity, of course, peculiar velocity corrected, gives me Hubble constant. It's a very simple equation to use to get a very clean measurement. And you can possibly imagine if any of these goes wrong, I'm in trouble. That's the exact place where it becomes extremely challenging to get a nearly calibration-free Hubble constant. It doesn't exist. So what can gravitational wave brings to us? Thanks to Bernard Schulz in 1986, where he showed for the first time that gravitational wave sources can measure luminosity distance without doing any calibration. The fact that objects which are heavy will fall faster, and you can actually calculate how objects' time scale of evolution and frequency is happening, which depends upon mass, and how much gravitational wave is emitted, how bright it is depends upon both mass and distance, also other parts like inclination angle. But when I fold this all together, I can get a direct measurement of luminosity distance without any calibration. That means I do not need a distance ladder. I make a measurement of distance. I don't need a ladder to go to high redshift. Great. Is it possible? Yes. Thanks to JWST, the only multi-messenger event with gravitational wave detected until now, conformably, has made it possible to see the gravitational wave signal and an electromagnetic counterpart from it, help in identifying the host galaxy, host redshift, after correcting for the peculiar velocities, so this has enabled us to make the measurement of Hubble constant for the first time. Of course, error bars are very large and not very precise yet because it's only with one event. But that's not the only story. This is the analysis which shows, this is the first analysis which has shown how LIGO India will play a role. This is a work done by one of the undergrad, Harshank Nimankar. This is a master's thesis, where he has done the analysis. So anything with I is with LIGO India. These are with the next generation gravitational wave detectors. What it tells us is that we will be able to achieve something like 2.5% measurement of Hubble constant using bright sources such as neutron star, even with LIGO Virgo Kagra and LIGO India, with about 50 sources. We have one now in last 10 years. You can do the math how it is going to be. Of course, our detector is going to improve. We are going to see further. More you see, the volume increases. We are going to see more events. So it is not going to be one in every 10 years. No, that's not what I'm saying. What I'm saying is it is not event which you see every day. But there is possibly stuff which you see every day. Those who follow gravitational wave community, you know some things appears every day in our detector. These are binary black holes. Much more numerous in number. Thanks to our latest release, we have about 176 LIGO black holes discovered with in JWTC4 until 04A. Unfortunately, those are not the sources with electromagnetic counterpart, and we may need to worry about something more to it. For measuring Hubble constant, as I showed you, it's a ratio of two quantities, redshift and distance. I can get the distance, so what? How will I get the redshift? If these are the sources, kind of my map of the sources I have seen, and these yellow dots or stars are my black holes, as you can see, I have put them not so randomly. I have put them randomly, but not uniformly. It will be corrected. Why not? Because if I put it in a map of a large-scale structure simulation, they are not going to follow at a place where there is no structure. They are going to follow a place where there is structure, where there are galaxies. Stars forms in galaxies. Black holes are expected to form in galaxies, and there is going to be a underlying clustering between black holes and galaxies. Remember, all black holes are not detected with very high sky localization, but we do indeed detect some of them. Until JWTC3, we have about 8 events which are detected with a sky localization error of less than 30 square degree. This number is going to improve drastically with the help of Kagra and LIGO India in operation. That's one of the main science case of LIGO India, that it will enable doing precision science with gravitational wave astronomy by particularly improving the sky localization. So what else? So now you have two friends who can see the same part of the sky with very different abilities. One sector sees the sky in distance, black holes. Other sector sees the sky in spectrum of the redshift of the galaxies. Do we have such surveys? Yes, thanks to DESI survey, thanks to SPHEREx, which has been launched recently, and of course Euclid, LSST, and so on. So if we can make a marriage between these two sectors, we get cosmology out of it. And that's what is going to come. This is called the clustering redshift measurement, has been demonstrated for the first time by in us and followed by several other works, which tells you that if I take different luminosity distance band and cross-correlate with the redshift surface of the galaxies, I will make an inference of the clustering redshift. Combining this in tomography with different gravitational black holes, I can make a measurement of distance and Hubble constant.
It is also true for primordial black holes?
It's true for anything that gravitates. Anything that gravitates will naturally lead to clustering. Bias parameter will change. We can discuss about it a lot. That's one of the works. Yeah, but this has been first time demonstrated on data of JWTC3 by 4 of us. This is the first inference of Hubble constant from binary black holes of JWTC3. Weak, but we are getting to a better measurement in future. This is the work done by that time I was a postdoc, and work was carried out by a master student, Cristina Diaz from Spain. We worked together towards this particular technique to demonstrate how this thing works. This is about 4 years back, 3 to 4 years back, where we have shown that with the help of LIGO, Virgo, Kagra, 5 years of operation, with spectroscopic DESI survey and SPHEREx, SPHEREx is nearly spectroscopic. Lower shift is very good, and most of the gravitational waves we see are at lower shift with higher SNRs. As a result, I can get to a good measurement of the cluster redshift and Hubble constant to about few percent, 2 to 3, depends upon the population, to measure the Hubble constant, along with how it traces the underlying galaxies. Coming to what Shubhi was trying to indicate, is about the gravitational wave bias parameter. This is a parameter I do not need to introduce much to this community. Bias is something you all deal with. Gravitational wave bias is a parameter which tells us how different population of astrophysical black holes or primordial black holes will trace the underlying matter distribution. We can measure it, and we can also measure the redshift evolution of it, which is parameterized by alpha. Now we have an entire method pipeline work, and many of my PhD students are working on this, which has demonstrated how using cross correlation and of galaxies with gravitational wave catalog, we can get to a measurement of Hubble constant using sources which we detect every day. Okay, I have a source which I can go up to high redshift, measure distance very well. Why should I just stop at Hubble constant? No, we will not stop at Hubble constant. We will do something else, of course, where calibration is again important. Those who work in the area of expansion history inference from observational data knows it very well how much astrophysics impacts even the dark energy inferences. So how are we going to do there? This is done by my student Afroz for third generation gravitational wave detector. Third generation gravitational wave detector will see much farther away with a precision on luminosity distance by at least a factor of 10 or so more. More sources, better in precision. What it allows you, this is a plot where both dark siren and both neutron star black hole and binary neutron star for bright sirens are included. It will make it possible to reconstruct the dark energy equation of state in a model independent way across redshift. I have another plot to show if you have questions. This is a plot which tells us what is the derivative of dark energy equation of state. That's the parameter we want to measure as a function of redshift. And it makes it possible to get to a very high precision measurement of Hubble constant, which is calibration free. There is no distance ladder. How does it compare with any other surveys coming up? On this side, we have all surveys which are coming up from DESI, Euclid, pessimistic, optimistic, W1 is Raman, baseline and extended, in comparison to bright sirens, binary neutron star and neutron star black hole, and binary black hole cross correlation with DESI and LSST. I'm coming there, yes. So the lightest shade here is the one for which I assume 1% of these sources will have electromagnetic counterpart. Why do I care about it? Try to understand the problem. I have an electromagnetic counterpart along jet. Jets are very rare to see because they are pointed. So I may be able to only see from the afterglow. Everything I do not able to see because I have an efficiency. All telescopes, science case is not about measuring electromagnetic counterpart of gravitational wave sources. So there's a duty cycle, there's an effect, thank you. As a result, our efficiency of detecting them depends. So this is a focus plot which tells us what is the science case. If I throw my telescope time, do I get anything useful or not? The answer is yes. When you compare them with the bright neutron star, which is the population of star formation rate included, and so far what we know as the astrophysical population is included in this analysis. What you can find that we will be able to make precise measurement and accurate, hopefully, if it is a calibration free, much better than several other surveys for bright sirens, and at the same level as other surveys using binary black holes. Why at the same level? Because the redshift error becomes the main bottleneck. Redshift error over here plays the major role in over here, and they really translates to a kind of a 1:1 error bar, but for BNS that's not the case. I may be able to get electromagnetic counterpart better. For different shades, you can see the corresponding color bar, how the error bars improves. More in number. So NSBH are heavier, we see further away. Lighter objects emit less gravitational wave, so it's difficult to detect them. Heavier objects emit more gravitational waves, so they are easy to detect further. Volume is more farther away, so it goes up.
And this is from current rates.
Right. Not 04, because the paper is published before 04A release. This is the with JWST 3.
But again, NSB also you assume some fraction has.
Yes. Okay. So the same convention, but also one more stringent convention. Heavier black hole comparing with a neutron star may not emit gravitational wave. Sorry, electromagnetic counterpart, because it will be engulfed. So I need to take a mass cut. So small as neutron star with a black hole of 5 solar mass, fine, 10, okay, but around 15 and 20 it becomes so heavy to eat up everything. So you do not see the electromagnetic counterpart. So that cut is already implemented. Okay? What we didn't say is good. So now I have a way to do a calibration-free dark energy equation of state measurement, not only about W0 and WA. Please remember, these are parameterization which is great at low redshift, but not so good at high redshift. There are papers on this already by multiple people. In this paper, we show that we can go up to high redshift and do an entire reconstruction of dark energy equation of state beyond W0 and WA. Okay, how am I going to time? I have 8 minutes. Oh, good. Okay, so that's all about the expansion history of the universe. Cosmology don't end there, right? Cosmology is about, for us to know about the entire universe, how possible it has formed, evolved, and come to today's state. And as I told you, there are open questions from Big Bang to black holes. How about the black holes part now? If you now start comparing of this mass spectrum and frequency spectrum you observed with gravitational wave detectors, as I said before, low mass connects with LIGO, Virgo, Kagra, high mass connects with PTA, and in future with LISA. So let's start and try to understand how we go over here. We want to understand where and how the black holes are forming. In this particular image, what is the exact history for them to form and evolve is an open question in the community. And on this, LIGO has started seeing sources farthest away for the very first time. We have started seeing binaries very far away in the universe than ever before LVK was operational. This is a plot made by Afroz again on mass versus distance. As you can see, we see sources very far away, as I promised you, so cosmological distance sources. Objects are pretty heavy. Crosses and dots are JWST 3 and 4, and the colors are their spin. These are the physical parameters that I can measure. It's like when you talk about a CMB researcher, they'll tell you I can go and measure at an 1 angular degree angular resolution what is the fluctuation in the temperature. This is a quantity that I measure on the sky. These are the physical parameters that I can directly measure from gravitational data: mass, distance, and spin. When you have this, think about a bit bigger picture. You have possibly seen some version of these plots in terms of posteriors and combining the posteriors. But is that the only way to do it? When I have a bunch of stars, I don't only combine their mass distributions. I try to understand what is the correlation of the mass of the stellar properties, and such a plot exists called the HR diagram. Let's try to understand that in terms of black holes, and this is the first work showing the phase space of binary black holes. A work led by Afroz as a function of the observable quantity. You write your phase space in terms of the observable quantities. And here, these are your first generation black hole population model, second generation black hole, the red ones, and also the primordial black holes. As some time back Suvir was asking, if primordial black holes form in the early time, they will accrete mass. They become heavier and they will start spinning because they are accreting mass. As a result, in the mass and spin axis, they start growing. And the number density is going to be different at the evolution and the distance trajectory. As a result, I can now have a phase space demonstration of the binary black holes. Please go ahead.
Which mass are you assuming as
Good.
starting point for the
these are subsolar masses. So they become of the order LIGO masses, or few tens of mass, or of the order 1 solar mass, after accreting mass in the entire history. So they accrete very slowly in the beginning. As they become heavier, they accrete more. As a result, the slope is very low here, and it grows later, and that's what you have seen. So this is for a very specific mass range. I can have all possible mass range. That's the exact predictability. All different black hole masses and properties will have different trajectories in the phase space. These are physical space you have. So what? Putting that on the current LIGO data gives us the measurement of the probability of these different formation channels for all different events. This is done for JWST3, also done a couple of months back by JWST4. So this is in second generation, anything in the AGN. This is the first generation. And to answer your question, whatever you see as gray are the places where none of them are too good. So we are of course not confident to tell it a primordial black hole, but we say that none of them are too good, and it's a gray region, and we say that corresponding probability. Okay? So that's our current state of the phase space of binary black hole distribution. What we go next? One of the open questions to understand is how binaries are forming. Are they forming by merging? Are they forming by accreting? If they form by merging, they will emit more gravitational wave than by accreting. So natural question to ask, what is the binary black hole mass spectrum as a function of redshift? This is a PhD work done by Christos, again from Spain. Apparently both the students are from Spain. Where he has shown in his PhD thesis for the first time that black hole distribution in LVK JWST3 shows some evidence of redshift evolution. This is a plot for different redshift bins. This is a kind of cutoff we see, not too early to be a 5 sigma of course, but that's because there are overlaps in the posterior, but this is the indication. You know, like when you make a 5 sigma, you start from 1. So this is at a very early stage first measurement happening. Where we go next? With JWST4, now there is a very strong evidence that there exist 2 different population of binaries in the data. 3 papers have come out together. Very similar conclusion. This one is again led by Afros, which shows us that black holes which seems to be spinning higher are apparently more massive than black holes which are spinning less for both heavier binary black hole and lighter binary black hole. And this cutoff is at the 3 sigma level is a pair instability lower mass gap. Means first generation black holes likely to fall up to these masses. So how are we seeing it? Thanks to the phase space, we are now able to distinguish between different observational sectors. And this will improve a lot with the help of more sources in the coming years. How about sources are far away? We are only talking about LIGO sources which you have seen as high SNR above 10 or 12 and so on. But there are many more far away, and they contribute to your stochastic gravitational wave background. Please remember, these are binary black holes which are coming from individual sources, but they are very, very difficult to detect individually. That means that physical properties don't change, no? Objects which falls, heavier objects falls faster, lighter objects fall slowly, they emit less gravitational wave. As a result, there is an intrinsic sporadic nature of the gravitational wave of stochastic background of astrophysical origin. This is a smoking gun signal which will distinguish from cosmological sources. Cosmologicals are not going to be like this. One of the persons who has also worked is SNeIa on this. At some point we have worked on this. So this is Mohit Raj Shah who has done this work. This is one of the works of his pages. He says where he has shown first time that there exists a unique covariance matrix, theory covariance matrix, depending upon the non-Gaussian nature of this signal. And if I can measure it, I can basically start putting a measurement of what is the population of binaries forming at the high redshift. Or what is the main take home? The take home is if the objects are very heavy, signals will be shorter. If the signals are shorter and more numerous in number, I can count and put a constraint. That's the number we go for. And this is a measurement made by him as a function of masses for both astrophysical black holes and primordial black holes nature. So now we have a constraint, time up. Okay, sorry about that. So that's what we have from High-Redshift. I would like to show 1 or 2 slides on the nanohertz, which basically I would like to tell you that the story is very interesting also in the nanohertz regime for supermassive black holes. How heavy and what are the formation places for these black holes is very important. I will not go to these details. What you have to understand is a problem which combines several length scales, from gigaparsec scale to parsec, sub-parsec scale for black holes to merge. And we are able to combine simulations of the state-of-the-art from MySQL, Romulus, and this is more analytical to come up with the theoretical signals. Let's take the main plot, what it's about. We can now start talking about how supermassive black holes are possibly evolving with redshift and masses. Are there more supermassive black holes at a higher redshift than at a lower redshift? This is the place where interesting measurement will be happening by both spatial anisotropy and average gravitational wave signal on the sky. This is the gravitational wave error distraint as a function of frequency. Ask me more questions later. I think I'm annoying the chair already. I would like to finish by saying that this is the first upper bound from the 15 nanohertz gravitational wave data and galaxy survey DESI. Paper is in the collaboration going soon. 2 weeks from now, it will be on archive. This is the first upper bound available from the current 15 years nanohertz data and DESI catalog released. With this, I will say that the future is very bright on this area. This is somebody was asking question about SK and the contribution future coming from TIFR side. My student Mohit is leading this particular effort of how Square Kilometer Array with galaxy surveys will be able to make first discovery of black hole evolution of the mass range of billion solar masses by combining SK observations of nanohertz signal. Summary. It's an exciting time to study the universe, this exact diagram using stellar graveyards. And we should not forget there are many experiments coming up, funded, and thanks is a really scenario of multi-messenger, multi-wavelength studies of the universe. LIGO India is coming up along with other detectors, which will be helping us a lot in improving the sky localization, along with SKA, which also India is a part of. We have heard yesterday's talk. And we'll be able to see much farther away than what you are seeing now with binary neutron star. This is my group whose work I have shown, and I will just finish here and take questions. Thank you very much. I'm really sorry for taking more time. I see a question.
Do you have plots from the paper with Alex where you actually did the H0 calculation? So when we were looking into this cross-correlation business, one of the issues we were running into is that we seem to be limited by the localization of the gravitational wave sources compared to anything in the galaxy catalogs.
Agreed. Completely.
And what was happening is that when we injected gravitational wave sources, the recovered posteriors were often not centered on the actual sources.
Individual posteriors will never be centered.
So is that the limiting systematic in your study as well, or what do you think is the...
Okay, no. Punchline would be the following. Don't use sources which are more error dominated. Cosmology of H0 will be driven by the best.
Did you cut?
Yes. Okay. So you basically make us SNR cut of 20 and above, so that your sky localization errors, you wait long to get the best and get the good measurement, instead of getting a many and getting a broad, not so peak error. So yes, this systematic is skilled by observing more.
Thanks for the very interesting talk. Can you elaborate a bit more on just this last bit about supermassive black hole genealogy?
Yes, sure.
And how are you getting there? How far we are from understanding?
That's right.
But especially, what's your idea? Do we have a hint at the moment?
Good. Let's break the questions into pieces. First is, where are we getting into it? So let's put the big question at first. What we do not understand. We do not understand the ecosystem of galaxy and black hole formation. We don't understand it. It is good to understand it, because if you want to really understand structure formation, this is an open question that you want to understand. Good. How to understand it? I can see a few black holes very far away thanks to quasars or AGN. May not be the only way. Another way happens when the black holes merge. So now you can ask about the question, there's a long-standing problem, no? How supermassive black holes are formed? Are they forming by accreting or they're forming by merging? There are two potential challenges. If they're forming by merging and the corresponding galaxy mergers are happening, they will emit gravitational wave dominantly in the nanohertz range. Okay, that sounds interesting. Now, how can I measure this? So that means that now two questions coming. How heavy they are forming, initial seat, when they are forming in the cosmic time, and how they are evolving. These three questions, let's focus on this for now, and try to understand how this will come up as an imprint on my nanohertz gravitational wave signal. If they form early, they will be more numerous in number by volume, and they will be more redshifted. We contribute this side of the spectrum. If they are more nearby and fewer in number, they will be more sporadic, more anisotropic in nature. And how long it takes for the black hole to merge, the well-known parsec problem, is captured by where this peak is happening. If the black hole is releasing a lot of energy by interacting with the ambient gases by dynamical friction, this will happen at an earlier, lower frequency, earlier time, else later. This we capture from several simulations. So this last piece nobody can capture, or we'll capture someday when we have quantum computers. Right now we capture using Romulus up to certain parsec, how we identify the black holes, and we try to now understand how many and how heavy they are forming. So remember what is in my hand. I have anisotropy as a function of frequency, and I have an average signal as a function of frequency. Now I want to understand the synergy with the galaxy surface. What's happening at the high redshift part, I start getting galaxy map in a tomographic way, and I can start having a correlation between them. And that's what this is shown over here, that heavy black holes sitting in galaxies, if there are more black holes at the higher redshift, they'll see more correlation than the lower redshift. So the map will be more homogeneous, more Gaussian than heavier black holes, right? Also we know from standard model, heavier black holes are fewer in number. As a result, they become more sporadic, means more anisotropic. So I have now two different probes. I would like to know how the shape of the spectrum looks and how anisotropic it at different spectrum. Combine all information. That's what you get. This is the omega GW. This is the correlation of galaxy with GW. This is the combination of the both. None of them are good alone. None of them are good enough alone. One is good in telling how rare it is. If they are more rare, more anisotropic. Another tells me how deep it is. If it is more in number, they are more brighter. But when you combine both of them, you get a very good constraint. And there where the next area or next frontier, in my opinion, is coming up, where I will combine nanohertz gravitational wave signal, which will be detected from many pulses from SKA, along with galaxy surface already planned or coming up. So you can now have a completely independent way to see these black holes. And as I couldn't show you that work, we have, so there's another PhD student from Canada, Vida. She has done a work where she has identified the host galaxy. I'm sorry if I'm taking really more time, but no. I do not have that particular slide. Sorry. So Vida has shown that how the host galaxy properties and the black hole properties will match, and we can do also surveys from optical and infrared. I hope that answers the question.
Yeah, I have another question, but we'll ask later.
So maybe we can, okay, maybe one quick question.
If we have this nanohertz, we are capable of detecting nanohertz gravitational waves, would we also see perhaps some cosmic gravitational wave background, perhaps?
Yes, sure. Gravitational wave, don't know. I mean, it is everything is there in the data. It is us on making best techniques to find them out. So yes, there are potential scenarios where cosmological gravitational wave will exist. That they are going to be very different in at least some of them in shape, but are not in the anisotropic nature. Very fact that was formed in galaxies, at least the Gaussian cosmological signal are likely to be more isotropic, makes it a possible different way to identify and distinguish them. But may not be right now, but in a couple of years after SK is available.
Okay, so let's thank Suvodip.
I'm really sorry for taking more time.
The next speaker is Susmita, and she showed me her title, and I just still forgot this. She's going to small scale structure issues and things like that.
Please go ahead. You can keep it here. You can use this. Yeah.
Do we have your consent to record your talk and put it up online?
Okay.
There's the microphone.
Press this one.
All right, so so hello everyone. So firstly, let me thank the organizers of this very unusual conference that we are having here today. And I also thank the organizers for letting me adjust my talk topic. So for this conference, I really wanted to be a representative of small scale structure and talk about what we can learn from about cosmology and fundamental physics from understanding the nonlinear structures where we think most of the dark matter is essentially. In particular, I will be focusing on dark matter halos and what, in some sense, we can learn from them. So at this point of time, I think after over the past few decades, we essentially have various different avenues of evidence that to understand our universe, we need a dark component to the things that gravitate in the universe. We need a dark component to the gravitational mass in the universe, and there are various different avenues from which we can test this assumption, right? Of course, it began with trying to understand the virialized structures of galaxy clusters, to understanding the rotation curves of galaxies, and then additionally, even in the 70s, there was evidence from measuring thin disks, and so those were the early evidences that we need this extra component of matter to understand the structures that are forming in the universe and how they are and their dynamics. And now, since then, we actually have many other smoking gun evidence that we really cannot understand all of the dynamics and all of the structure formation that is happening in the universe if we don't invoke this dark matter component. So in the most standard paradigm, we understand that dark matter is cold and non-relativistic. We also think that most of our observations, particularly on the large scales, can be explained by thinking of dark matter as being cold, non-relativistic, and also collisionless, right? But while dark matter has been quite successful in explaining the standard model of dark matter in some sense has been quite successful in explaining the large-scale structure of the universe, when we, I particularly have been focused on understanding the conglomerates of dark matter, which are essentially the endpoints of cosmological structure formation. That is, these dark matter halos. These are essentially self-bound, we think virialized gravitational structures which has the highest densities of dark matter in the universe. And this is essentially the potential wells within which all of the stars, galaxies, all of the astrophysical phenomena that we see in the universe are harbored. So understanding the formation and structure of these objects also holds a lot of key to understanding the nature of dark matter, because these are essentially where the highest densities of dark matter you will find in the universe, and their detailed structure contains a lot of information about the exact particle nature of dark matter, and also in many ways the evolution of structure in the universe, and how galaxies have evolved within them. Right. So in the standard cold dark matter paradigm, we think we have many testable predictions. We think structure formation proceeded hierarchically. Small structures collapsed collapsed down to the small scales, and they merged to form larger and larger structures. And within these collapsed structures, if they were able to retain enough gas, form stars, is where we form the galaxies. Okay, so these structures then host galaxies essentially from the dwarf scales to these structures can hold astrophysical objects like galaxies that are in fact orbiting in the potential wells of these large dark matter halos. So essentially they span a wide range of things that we can observe directly even in light. Of course, in the left end is structures that could never form stars or have stopped forming stars and are today completely dark substructures. So what I have been interested in is to understand the internal structures of dark matter halos, and in particular I have focused significantly on understanding the boundaries of dark matter halos. So typically we think dark matter halos are essentially regions which encompass about some threshold or some matter which exceeds some threshold of the background mean density of the universe. In particular, they were typically defined as containing, as being sort of these not black blocks, sort of these structures that are nonlinear, kind of disconnected from the Hubble flow, virialized objects that are encompassed within, say, 200 times the matter density of the universe. But depending on who you're talking to and how you try to understand where, say, the influence of this object ends or what is the boundary of this object, you could be probing actually very significantly different regions inside of these structures, right? So this is a figure from figure from an n-body simulation of a dark matter halo, and on the right-hand panel is a figure from is a density profile of a dark matter halo, and these have been studied quite extensively, both through n-body simulations and also in many ways through observations. However, if you so this is the general space in which we look at dark matter halos. However, if you look at another way of thinking of the internal structure of dark matter halos is to look at the phase space diagram of these objects, right? And I particularly like thinking about this because it tells us that the structure within these actually can encode very interesting ideas of how these gravitational systems collapse and form in the phase space scenario. So, for example, in around a typical dark matter halo, if you were to look at the velocity versus radial space, which is what I'm calling phase space for the purposes of this talk, the structure around the halo can essentially be divided into essentially three very distinct regions. Okay, so far from the halo, so v over here is the velocity with respect to the center of the object. If you're far away from the center of the halo, you're in a region where far away from the center of this potential well, you're in a region where the universe is essentially expanding with the Hubble flow, so you have positive radial velocities. As you move towards smaller and smaller radius, you reach a region where things are turning around. So they are, because there's a potential there's a potential well at the center, you cut off from the Hubble flow, you turn around and start falling into the structure, and your velocities, of course, become more and more negative. You come to a region where you have this infall stream, and eventually, as your orbit is eventually going to get bound, you start orbiting in this multi-streaming region of the object. So this multi-streaming region is typically what we think of as the internal region of a dark matter halo. And in fact, the outermost, so you come in and essentially you start orbiting. So the part of your orbit where you cross pericenter, and then you are now reaching, go to the other side of the center of the halo, and you're reaching the first apocenter of your orbit. The region that is created by the first apocenter of the most recently accreted material is a clear boundary, which is a clear boundary that separates two very distinct regions of the phase space, where you have multi-streaming versus single streaming infall into the halo, right? And essentially, while we think of this, the inner structure as these phase-wrapped multi-streaming region, the inner structure, why this is interesting is actually there are ways observationally to actually access this. In particular, while this is taken from an idealized spherical smooth accretion simulation, in particular, even if you move away from this idealized scenario of very smooth spherical accretion, you also while you're going to mix up, you're going to basically smear out, because your initial density peak that you're not collapsing into is not going to be completely spherical. While you smear out the features, the phase space structure starts to encode significant, interesting structure even within it, right? So of course, this is the phase space. The integral along the VR direction gives you the density profile. In the spherical case, we've all known from Bertschinger similar solutions that we should have these very sharp caustics. And even if you start with a non-spherical patch, while your caustics, of course, get smeared out, the outermost caustic actually remains quite distinct even in the aspherical structure. So this distinction between what is outside the halo and what is inside the halo, what is multi-streaming and what is single streaming in some sense, persists even when you average. Not only in these idealized simulations, if you go into n-body simulations where you have halos that form with a variety of accretion histories in a variety of different environments, if you try to, say, for example, club together all halos of a given mass, you still see this phase space structure persist, and this separation between the multi-streaming and the single-stream region persist even in this kind of an ensemble average thing. So typically, halos have been thought of as these virialized objects with an NFW-like profile that describes them quite well to a large extent. But actually, over the past few years, we have begun to understand that actually there is a significant deviation from these NFW-like structures, not only just, not even in the theory space, right? So for example, this is a density profile of a stack of cluster mass halos from a simulation, and the bottom panel is the slope of the density profile, so the logarithmic slope as a function of radius. And your NFW curve over here is this dot dash line. And you can see that near the, what we traditionally define as the virial radius, you see a significant deviation from this NFW-like profile, where the density profile can become much significantly steeper than the -3 that you expect, right? So this is stuff that we've been thinking about for a while, and essentially, it's telling us that there is more to think about in the dark matter halo, even within the context of cold dark matter. And it is, I think, interesting because what we found is that this steepening of the profile coincides exactly with where this boundary of the multi-streaming and the infalling region of the halo is.
Could you just remind me
Yeah.
exactly how our veer is
Here, RVIR is defined as 200 times the background matter density.
So in this particular case,
It's been.
might not have anything to do with RVIR.
Sorry?
R200 may not be RVIR.
No.
You make a dynamical definition.
That's true. Yeah, if you make a dynamical definition, it'll come out to be somewhere in 350-ish over density in the dark matter universe. I think this is defined as 200 in this particular plot. But yeah, it's defined based on the over density. Yeah. So here it is very close. It's not that it's it's dramatically different from R200 or something.
Putting it another way, halos
Yeah.
have been completely misdefined over the years. Anyway, go through.
Okay. Yeah. And right. And yes.
Maybe it's a half-topic question, but how do these features change with angular momentum of the halo? Is there everybody like looked into limestone?
Angular momentum of the halo particles.
The total, the halo will have some angular momentum. Do these things vary significantly, or are they constant?
The angular momentum will be small, but generally also even the gravitational orbits will primarily be the internal rotation actually does not matter to set the orbits of the particle. The particle angular momentum will of course affect the size of the feature. So not all your particles come in with the same pericenter distribution. So there is a distribution of pericenter. So that sets a thickness to this feature. But the overall rotation of the halo should not change the internal mass, essentially. The triaxiality does matter, yes. I don't think that's what you're asking about, rotation or triaxiality? Triaxiality does matter, yes, of course, the triaxiality does matter, yeah. In different directions, you will actually reach the apocenter at different distances, yeah. So what we are plotting here is a spherical average, yes. Yeah?
Yeah, I have a few naive questions about how this corresponds to real galaxies. Do these halos you consider have subhalos inside them? And
Yeah.
are those subhalos something I should think of as associated with maybe
Galaxies?
clusters or something like that within the galaxy?
Galaxies. So essentially, we think that subhalos will host galaxies within them. Yeah. Galaxies. Globular clusters is a different density scale. Yeah.
Halo here corresponds to a galaxy.
Halo corresponds to a potential well. There will be a galaxy in the center, but because you have hierarchical structure formation, you will have a halo is formed also by accreting smaller substructure. Okay, so yes, yes, yes. So this halo essentially will have diffuse dark matter as well as clustered dark matter, which we will call subhalos essentially. Yes. So maybe I have a picture of this somewhere in the next slide, so it'll be clearer. Yeah. So this structure essentially, if you look at the outer regions of the dark matter halo, and because we are saying that this is the most recent apocenter of the recent of accreted material, it also changes as the function of how fast the halo is growing. So if your halo is growing faster and your potential well is deepening faster as you are going from pericenter to apocenter, you will move. You will reach apocenter at a smaller distance, right? So it is a function of accretion rate in units of R over R200. It is also a function of when the halo formed. It is a function of the redshift. So essentially, this detailed structure of the density inside of the dark matter halo, what we are calling the splashback radius or the edge radius is the minimum of the slope profile. Contains a lot of information about the overall evolution history, triaxiality, and the structure of the halo. In fact, I should point out that not only does just the location of the splashback contain this information, of course, as you can see that the entire profiles of these objects change all the way to the inner region, and you can also see additional features. Right. As Ramesh was asking, am I thinking of these halos as one galaxy and one halo? But because you have hierarchical structure formation, particularly in cold dark matter, you have a large potential well, but you have that potential well in some sense has also grown by accreting, by mergers of smaller and larger objects. Okay, so you not only do you have diffuse dark matter particles orbiting that potential well, you also have substructures that are tracing that potential well. So you have, so for example, if you think of a large halo, you will have a central massive galaxy which lives inside its own subhalo, and you will also have smaller structures which each of them will have their own galaxies orbiting that central potential. So all collisionless components inside dark matter halos, in fact, show this kind of, should have this feature which embedded in its density profile, which is basically tracing this boundary of this multi-streaming to this infill region. Okay, so for example, this again is from a simulation. The black dashed line is the dark matter splashback radius. So if you just took the dark matter density inside dark matter halos and looked at their distribution, you would see it here. And these are the number density distributions of substructure inside of orbiting that same potential well. You similarly see a feature. But substructure, unlike dark matter particles, experience tidal forces, dynamical friction. So there are interesting things that you can probe with that. Yeah.
Have you looked at, like, if you add the galaxy formation? Because I mean, like, one thing in galaxies, when they fall in, they experience quenching and all sorts of stuff. So would that change its profile?
Yes, I will get to that in observations. Great. Yeah. Okay, good. All good questions. Leading up to next parts of my talk, so that's convenient. Yeah. So this internal structure can act as a strong probe of various different evolutionary history and of particles and subhalos in different ways. Right. So just a quick overview. Why do we care about splashback? Why do we care about the internal structure? Particularly, this boundary that I'm talking about is very simple to understand physically. Okay, so it is basically, it is set by solving for orbits of particles that are collapsing into a potential well in an expanding universe. It is made of particles that is coming in the most recent accretion. So this material is not yet deeply phase mixed. So it is easy to understand this boundary, which is why we focus a lot on where this deep feature is. And one of the reasons it is very exciting to me is, of course, that it is also accessible observationally in some sense. Of course, there's, this outermost boundary is what we call splashback, or the first apocenter. But in fact, if you look at dark matter halos, if you stack them in curious ways, you can also often see, even if you don't stack them, you can often see additional phase space caustic-like features that actually show up even in simulation halos, which have grown through very varied evolution histories. For example, here is an example of the second caustic showing up inside a dark matter halo. Right? So if you have collisionless dark matter around a galaxy, this is like a fundamental scale that should show up at the edges. There is also fundamental time scales attached to it, and it is accessible observationally. So it's always interesting to think about what we can do with it. Right. So as I was saying, we also, some of the work that I've been thinking of, and since we were also discussing about machine learning, and I'm not yet using it for cosmology in some sense, but because the internal structure of we typically think of them as being uniform virialized structures, I was interested to go and ask this question and because oftentimes we see more than this uniform multi-streaming structure inside of the phase space of dark matter. I was interested to go and ask, can we actually separate without labeling, without using any predefinitions of boundaries, etc., can we actually try to separate interesting clustering in higher dimensional spaces within dark matter halos? So I will not go into the details of this, but just as a quick example, we were looking at these UMAP methods, which are basically manifold approximation. It's basically a dimension reduction method. You take some higher dimensional data, and you represent high-dimensional clustering in a low-dimensional space. And we were asking if, how is the structure of dark matter halos? Are there natural boundaries and clusters that come inside of it? So it basically makes a graph in higher dimension and finds clusters using that graph and then represents it in a lower dimension in a way that it preserves the topology of the higher dimension. And this process is done, this projection is done in a learning process. But essentially what we did with the student at IISER Surya is we just took the 6D phase space information. We've been studying these objects for a long time. We just took this 6D phase space information and used this UMAP clustering on UMAP projection method to see if there are natural boundaries or natural, or maybe it's not natural, if there are boundaries that stand out to us without adding any predefinition. So, we do like beautiful pictures in astronomy. So if we take the full phase space of dark matter particles within, so this is a Milky Way zoom-in simulation of a halo out to 5 times its, roughly about 5 times its virial radius. And we took the entire 6-dimensional phase space and got the UMAP projection for it. And basically, this is how it looks. So in UMAP, what it does is it separates out different classes of things that are close together in a higher dimensional space. So these are different classes of objects in this entire region. So what is this? What is the largest cluster? What are these other things other than the fact that they look really nice? And
what metric do you use?
here we are actually using a flat metric. We are not used for the distances. No. What do you mean?
You have 60 phase space.
Yes, we do.
Velocities and positions.
Yes.
So how do I define distance in phase space? There's some distance.
You can
metric.
define a distance in a 60 vector space, right? Yeah. So they're scaled by their virial velocity and virial radius. So you get it from 0 to 1, and then you define distances in the 60 space essentially. Yeah. Right. So this is your cluster. So what do we see? So what is this largest cluster corresponding to? What are these external structures corresponding to? So we do an additional method of dB scan to actually isolate the particles that live in these clusters. And we take these UMAP projections and ask what are the classes of particles that end up in the largest uniform identifiable object in this space. The alpha 1 and alpha 2 by themselves don't have any deep meaning. They're a nonlinear mapping from the high dimensional space. So we take this cluster and go and plot it in the actual XY space in this universe. And you can see that this is the Milky Way halo. These are the largest cluster in this UMAP space. Orange is where the particles belong in real space. This is the typical R200M, I think. And this is essentially where splashback radius is, so the entire multi-streaming region is. And what we first stands out to us that actually the halo is not a uniform structure. The entire thing, even within the multi-streaming region, which we club together as being a single virialized object, it does not comprise the largest uniform object in this higher dimensional space. In fact, we find that almost 30% of the particles live outside of this larger cluster. In phase space, we see that, again, this is the same orange particles which form the largest cluster in this projected space. And essentially, what we find is that they contain the innermost parts of the phase space. So if I take the orange part and plot it over here, these are the objects, and the part that does not fall into the largest cluster is shown over here. All right. We went back and asked, what does this mean? Of course, we had some intuition about what it might mean. And essentially, this is telling us this projection is mapping out, separating the older part of the halo, which we quantify by the particles having the number of pericenter crossings. So essentially, we have things that have had more than 2 pericenter crossings that live inside this region, and things that have had a single pericenter crossing live outside of this region. In fact, we find that things up to splashback actually don't enter this older part of the halo. So maybe what we think of this uniform sort of phase mix part of the halo which is actually naturally expected. It takes a while, it takes a number of dynamical times for particles to, in some sense, get phase mixed. And in fact, the most recently accreted material has not yet become dynamically uniform with the rest of the halo. All right, so I have about 10 minutes. I'll move away from that and, yeah.
So what you default in the center of the change depending on how you do this UMAP thing? I mean, there are some free
Yes, there are essentially 2 free parameters in UMAP, which is the number of nearest neighbors that you count in your clusters and the distance to those. So depending on how you choose that, it picks up global topologies versus local structure. So yes, so if you made your nearest kept making your nearest neighbor very, very large, at some point you would find the entire halo. But if you made it very, very small, you go the other direction. At some point, actually, you converge. You don't, even if you keep picking up more and more smaller things. So we did a convergence test in some sense. I have plots for that later. Yeah.
So what do you want to do with this UMAP?
Okay, so originally we had what we had originally wanted to do with it is to use this kind of thing to actually find substructure in dark matter halos and see if they separate out. So we are working on that. I think this was just, in some sense, this is demonstrative of seeing that, the entire halo is not virialized, and, and there are various ideas we have, also how to map the galaxy to this space and so on, galaxy colors and so on.
Particles which are not in the old part of the halo, we can think of them as smaller halos in the process of merging? Or they just, haven't completely...
Yeah, not just smaller halos. So a lot of it is actually substructure, but they're also dark matter particles that have just not had that many orbits, essentially. They've just, even if it takes some time to become, reach that adiabatic invariance and become disconnected.
If time permits, maybe a quick question just to understand. So from the phase space to alpha 1, alpha 2 space, what is the exact advantage in combining this? Like, phase space should be already informative enough.
Yeah, it is not as clear. It is informative, yes. So I do agree that we had some intuition about what we were expecting in this space. But it is actually very difficult to separate this out. I have not seen any easy way to separate out, say, the virialized part of the halo from the non-virialized. Yeah, so it actually just...
On a particular physical area.
Exactly. It maps to a physical area without us having defined any predefined boundaries. Yeah, and it maps to the accretion. It actually maps to the particle orbital histories is what was interesting. Yeah. Anyway, so I have less time. So of course, as I was saying, the understanding of this outer structure is fairly easy. Gravitational collapse and collision-less dark matter. So we've done various work trying to see how these, going back to the original outer regions, to understand how these affect different parts. I won't go to the details of this because I wanted to talk a little bit about the observations. So we've looked at how the splashback radius changes in modified gravity because you're changing the G, you're changing dynamical friction of how quickly the objects are falling and so on. Different dark matter models, of course, as you would expect, if there are additional, one thing that I work on along with Orko and others is self-interacting dark matter. If you have additional channels of energy exchange, it'll change the internal phase space structure, the number of streams and so on. And also, we also checked with changing W long time back. And maybe some of this we can revisit now. Okay, so I think in that part, I wanted to establish that the halo can be a dynamic complex object, and simple principles can help us answer simple questions about cosmology and fundamental physics. All right, how do we actually observe them? Yes, how do we actually observe them? We've been observing them in lensing and galaxy distributions. Lensing measures the actual dark matter inside this potential well, the total dark matter mass as a function of profile. Galaxies are tracers of this potential, so their density also helps us look, they also trace the phase space, they also trace the potential well, so we can see where the boundaries are. And we've been working on these clusters and measuring these profiles. Particularly, I've been involved with work with the DES. There have been colleagues of mine who have been working with HSC and so on to also measure the internal profiles of dark matter halos and measure, particularly focusing on the outer profiles. We've been working with the lensing and the distribution of DES galaxies around ACT-SZ selected clusters. And basically, we measure the density distribution in basically our delta sigma. So delta sigma is the excess surface density that you measure from lensing of background galaxies around, say, a massive galaxy clusters. So these are ACT clusters. Most of them are 10 to the 14 solar masses each inverse and higher, and these are stacks of those. So on the left panel is the R times delta sigma, and on the right panel is the slope profile that has been fitted using an underlying model that includes the sharp transition at the outer regions of halos. And we have in lensing, we have a good detection of the splashback radius. And additionally, we also detect this in galaxies, right? So this one is the distribution of lensing around clusters. Here, we are measuring the distribution of galaxies around clusters. And galaxies, unlike dark matter, are in some sense, they don't remain uniform. Rather, they evolve as they orbit through the potential of a halo, unlike dark matter particles. So they can come up with interesting features. They can show up interesting features in their distribution. So for example, one of the studies that we did with ACT cross DES galaxies was to look at the galaxy distribution as a function of the colors of the galaxies. And these are their slope profiles. So these are red galaxies, green and blue galaxies, or galaxies in the valley and blue galaxies. And we see very distinct differences in where the apparent minima or the apparent splashback is. We found that the galaxies and dark matter follow each other, so the lensing in the galaxies were consistent, not only at splashback, even deep inside. But I wanted to focus on this for a few minutes, as Nyash was asking. So this is answering your question. So essentially, as I was saying, galaxies do not remain constant as they orbit through the potential. And if galaxies particularly, change their star formation properties, if they quench as they orbit through the cluster, as they orbit, the galaxy colors could be changing. So their star formation rates could be changing as they orbit through the cluster. So this is a typical orbit of, say, a blue galaxy falling into a cluster. If their quenching time scales are of order, say, as they cross, of order of less than, in some sense, a dynamical orbital time scale, then essentially they never reach the edge of the dark matter phase space, right? So a blue galaxy will come in, and by the time it reaches splashback, it has presumably turned red, right? So their phase space boundary, the multi-streaming to the infall single stream, occurs at a different place compared to where the dark matter is, or maybe where red galaxies is. Which is why we thought we are seeing the shift in the location of the minimum. So essentially, the slope profile contains features, or the detailed density profile contains features that trace how long, that could be tracing how long these galaxies have been inside the halo. So we did this work to put some initial constraints on the timescales, quenching timescales of galaxies inside of clusters. This was done with a simple model with radial orbits. When we include angular momentum, it would introduce more complexity, and it would help us understand more about galaxy evolution and these things. This is data. This is the distribution of DES galaxies around ACT clusters. Yeah. So it's a cross correlation essentially. Yeah. And these are the data points. These we are getting from a model fitting. So these are, yeah. Right. Right. So yeah. So not only are we measuring, not only just focusing on splashback, we are actually measuring the entire profile, and with surveys like DES and LSST, we are going to be measuring the matter distribution inside of these massive objects with a lot of precision and accuracy. Yeah, I'll just take 2 seconds. And we can put very interesting constraints. One example I showed is with galaxy evolution. We've also been doing some work in putting constraints on dark matter across sections. Because, while, for example, the thing that we've been working on is self-interacting dark matter, and while we mostly focus on cores at the centers of halos, there's actually signals out even beyond the core for SIDM-like models. Because you're creating a core, you're pushing matter outside, so it actually ends up steepening the profile right outside. With current precision in lensing, we can actually start to measure these small differences even in the outer profiles, which are far away from the huge central galaxy that is sitting over there. So we put some constraints on SIDM models from cluster lensing for, I think this is, I know of the first work. We also put constraints on dissipative dark matter models and so on. But I wanted to emphasize, maybe in the last part of my talk, that we are in an era where we are really going to be, as Suvodip was mentioning, in many ways we are data weighted. We are getting really beautiful, precise data, and it's waiting for us to be as creative as we want to be with it. So we can really go ahead and with our new ways of understanding the dark matter structure, we can really start to ask more nuanced questions, even within the paradigm of cold dark matter, to test a lot of our predictions and so on. I wanted to show the results that I've been showing from data are mostly from cluster mass objects. I wanted to show briefly some very exciting work that I've been doing with my colleagues. I've been very excited about it because it's a new regime for me, particularly with Alex Amon, who's now faculty at Princeton. So we've been pushing to get the halos around faint galaxies and trying to see how well can we measure, say, the internal halo profiles of these objects. So we were looking at low-mass galaxies in the Dark Energy Survey at low redshift, and we wanted to see if we can measure the lensing profiles around them. We worked on a method that has been used within DES to measure redshifts by using self-organizing maps, by comparing it with redshift surveys, small patches of redshift surveys where you have both photometry and redshifts, to characterize the redshift distributions of these faint galaxies. And then we went ahead and measured the lensing profile. And I just wanted to show the lensing. So our stellar mass, estimated stellar mass for these samples are close to, are between 8 to 10 solar masses. So these are 10 to the 11, 10 to the 10 halo mass galaxies we expect. And these are the lensing profiles that we are actually measuring around them. And so these are the raw measurements that we have for delta sigma versus R. This is the comparison with CDM from n-body simulations and also with an NFW-like model. So I was really excited to see the number of points that we are getting actually in the one halo, in the internal halo regime, and also we are also measuring this transition radius very, very nicely. So these prediction plots are from CDM. Currently, they look quite consistent with what we expect from cold dark matter. And we also put some constraints on the halo mass, stellar mass relation at those mass scales. So I will end with that. I've taken a lot of time. There are many exciting directions to go to, and it's just waiting for people to take it up. Thank you.
In your UMAP, have you looked at the sensitivity of the results to the choice of metric in phase space?
No, we haven't tested that, yes. So I think he did test it. I think he was not getting a lot of difference in what we were finding, but we haven't tested that carefully is what I wanted to say. Yeah.
Thanks for the very nice talk. Can you go back to the very simplest model, the spherical halo?
Yeah.
So a couple of questions on that. So first of all,
This
so
one
forgive
will-
my, not when you plot against the, okay. But no, I think the next one. So when you plot against the radius of 200, R200, that plot on the bottom left,
Yes,
where
yes.
there is a radius of virialization. Now that is defined there, and also I have a question. So this is assuming spherical symmetry of the whole halo, right? So did you try to do something where you slightly modified, like you have something slightly anisotropic? Because after this, you pass directly from, embodied simulation in general. Yeah.
Yes,
So
yes.
something in between, like you introduce a bit of an anisotropy.
Yes.
Or three-dimensional structure.
Yes, so
What
this
happens
is
in
from
that?
simulations.
Yeah.
The virial radius are these, the virial density are these defined from the original spherical collapse model like object. So it's just what radius encloses, say, 200 times the matter density or something like that. But the other question about your spherical versus, so this is a stack of clusters, so it's basically doing a spherical average. I think this picture will probably show you a more, so you can't probably see them. The black solid lines are from a spherical calculation of self-similar infall into a peak, a self-similar collapse. And the colored density map is the phase space for if you have a non-spherical peak, essentially, and you do a self-similar calculation again. So as you can see that if you have triaxiality or asphericity, the streams start to show velocity dispersion. Now the dispersion is coming because you are averaging, you're still plotting in spherical coordinates what is not spherical. So they start to show that spread, and essentially it washes out. So if you just had clean spherical infall, you would, at every apocenter, you would get these caustics. If you have non-sphericity, you wash out these caustics, but the particles that actually reach the furthest out are still the ones that are on the most radial orbits. So actually the outer boundary is still well estimated by just the spherical calculation, but of course the profiles change very, have signatures of asphericity.
Thank you.
Yeah.
And on the interactive dark matter, there are claims that maybe that can form black holes directly from. So did you explore that, or what your comments on that?
Yeah, so I did not talk about that part at all. So now there are there's a lot of interest in the community to not just forming cores, but in special regions, particularly in tidal regions, halos can actually accelerate to a gravothermal core collapse, where you can form, which will should actually very quickly go to a black hole because it's catastrophic collapse. I haven't explored the black hole part, but I have explored core collapse to a certain. We can talk about that.
You had a slide where you mentioned modified gravity, and then I think the immediate next slide you had a couple of curves, one of which was GR. The vast majority of simulation images results you've shown have been with fully Newtonian simulations, right?
Yes, the typical.
So when you do,
yes.
it's not. Is it this slide or?
Which one did you want to see?
Yeah, this.
Okay.
Yes. So when you say GR, how do you do this? Like, what does the code actually do? Which code are you using?
No, so this by GR you basically mean that your background evolution is FLRW and you have lambda CDM. I think this should say lambda CDM. Yeah, these are Newtonian codes.
Okay.
Yeah.
Okay, so since we have to also get the picture clicked, so we just go downstairs to the north, and we can keep discussing, and then after that we have to have. Back by 11:30. 11:30.